We're going to talk about the Birge Vieta method. Alright, so let's start about it. The step-by-step procedure is given. You guys just need to follow it up. It'll be easy. I've written out the reasoning also, so it won't be that hard for you. So basically, you start by considering a polynomial Pn of x, which equals to the RHS as given, which is equation 1. Now, in this polynomial, I want you to know that a0 will not be equal to 0 and a0 up to an are real numbers. Yeah, exactly. Now, where p, if supposing we say that, like for instance, that if pn of x, which the polynomial is over there, if it and if we let p to be a real number, at the same time we will have to also find the approximate root p of the polynomial pn of x. So that's what we are doing over here. So now, if in the first case, if that p is a root for the polynomial pn of x, then pn of p equals to 0, which gives you equation 1, and pn of x equals to x minus p into qn minus 1 of x. Now this basically happens only when the small p is a root for the polynomial of pn of x. It's about that. Now supposing if p happens to be a root for the polynomial of pn of x, then as you can see, we get pn of x to be of the form x minus p into qn minus 1 of x plus r of x, where pn of p will be actually equal to r of p. It's actually an r which will be equal to 0. Now, this basically happens when p is not the root. This is the condition you will have to write, and yeah, it is a must that you write pn of p equals to r of p equals to r equals to 0 when p is not a root. But however, you will not be writing the same when p is a root. It's how it works about it. Now, for qn minus 1 in pn of x, where pn of p equals to rp equals to r equals to 0, I'm talking about the equation A as I've marked it. I need you to understand that the degree of qn minus 1 with the with of qn minus 1 is actually of n minus 1. Degree is actually n minus 1 of qn minus 1. That's what it is about it. So that particular qn minus 1 of x is written of this form, since the polynomial is of n minus 1, which I have written with some certain conditions, where b naught is not equal to 0, pn of p equals to r equals to bn, which equals to 2. That's what it is, and b naught up to bn minus 1 are real numbers. Yeah, they gotta be in real numbers in order for you to operate this, because that's what you need to know, because real numbers are the ones which can handle it right now. If you put p, now basically in the next step, we're just going to put the pn of x values and qn minus 1 x values in equation A. I've marked equation A. So basically you just put these values. It's not a bit much of a task. And we come to the other part of the derivation. Now, equation 2 basically implies this, alright? So that's what we got about it. And x minus p into this particular polynomial plus r. When you multiply x minus p into the terms that are in there, you obtain of this of a particular format. So first you multiply x, and then you multiply the p. However, you leave r alone, and then you collect the x terms together. As you can see, they're all like that, and you collect the p terms together up to the polynomial, and however you leave r as a constant. Next, in the next sense, we are taking xn and xn minus 1 terms together and clustering them together, and the last term that is only left together r minus pbn minus 1 plus r, because x, there's no coefficient of x left, there's no coefficient x which is actually there to be included in the other term, so it basically comes as a constant. Now I need you to compare the terms with the same power. By doing so, you get this step, which is obvious. You just need to find out the b1 b2 values from the procedures what I included, and you proceed on. By doing that, basically you get the value of r. That's what it is about. So now we are moving on to the next part in the sense the continuation of it. This is just a procedure to help you understand how we get b1 b2 b3 and so on. This particular synthetic division is not necessary for you to do it in the exam, but if you do this you'll be able to understand it. And this is how we obtain b1 b2 bk and up to bn, since I put the multiplication format for you in order to understand it, and it's much more easier for you to see it. And that's how it goes. Basically it's b naught into p, then it's multiplied to give you the term pb naught, and the sum of pb naught and a1 is what we get as b1. That's the particular thing which you can see is what I've written as b1. So that's about it. That's how it goes up to bn, and that's how you find out the value of it. Now for the value p, which is an approximate root of px, we need to find the value p. So in order to do that, we differentiate the kth term. By doing so, we obtain this particular term, and further simplification is done from it. And we go into the next part of the continuation, in which we get this particular term. The ck minus 1 is actually of this normal term. It is actually of this form. It is of this form. It's obtained from the second synthetic division which you do. It's basically that, but you need to know that ck minus 1 is basically of this value, so you need not actually work out the synthetic division for understanding it. And then you consider Newton-Raphson's method, which is given over there. I want you to put the value of xk as p, because it's basically what we're going to find out. And then we know that the value of p equals to bn from equation 2, but we do not know the value of p and dash of p. So basically what we're doing is just we're trying to find out p and dash of p. In order to do that, we're just considering the following polynomial. From that, we just differentiating it by the method of uv and plus uv method, uv dash plus v dash. Then you put x equals to p. Apparently that term would become 0, because if x is substituted in p, you would get that term. So we get this term. That's how we did it. Now if you put pn minus p, sorry, pn of p equals to bn and pn dash of p equals to cn minus 1 in the following Newton's-Raphson method of what I mentioned above, you'll be getting the formula xk plus 1 equals to xk minus bn minus cn minus 1 by cn minus 1, which is the required Birge Vieta method. Basically it's a whole derivation for you to run in an easy method. It's much more easy for you to go step by step, so you can play the video again from the start. If you like this video, give it a thumbs up.